Ah, welcome. What we're going to do in this video is go over the major concepts and a few problems as to what you can expect for the quiz on temperature and phase changes. This will not cover everything, but this will cover many things. And hopefully this could be used as a resource to figure out questions where you might be stuck. Quick review. Phases of matter. The most common phases of matter are essentially solids, liquids, or gases. I want you to understand that any substance can be any phase of matter depending on the temperature. The most common substance that we talk about is water. And if you think about it, the higher the temperature, the more energy, and the more movement in the particles of the substance. Try to remember those simulations where we saw the particles move around more as we put them over the heat. And when they were cooled, the particles slowed down. Well, how does the temperature relate to the phase of matter? Solids, where the particles are moving slow, have a definite shape and volume. If the particles were moving fast in a solid, they would be not having a definite shape. They'd be going everywhere else. If you have a solid, let's think of water. If you have ice, if you add some heat to the ice melts into a liquid. In a liquid, particles are flowing. They have a definite volume, but not a definite shape. As the ice cube melts, it will go and form a pool wherever it melts, and that shape is not clearly defined. If you put it in a glass, it would stay in the glass. If you put it on the table, it would cover the table. It will fit the shape of its container. And then gases, then if I took that water and I put it on the stove and I boiled it, added even more heat, and I turned that liquid into a gas, and then it made steam, well, those particles move even more freely, and steam has no definite volume or shape, or the gas of any substance. But this doesn't apply to just water. Any substance, any pure substance can be a solid, liquid, or gas depending on the temperature. So when I say phase changes, I want to be as clear as I possibly can. I need you to understand that here are the three main phases of matter: solid, liquid, and gas. This is such an important chart. I want to put it here because I want you to understand that when a solid turns into a liquid, it's called melting. When a liquid turns into a solid, it's called freezing. So the arrows indicate where it starts and where it ends. When a liquid turns into a gas, the word we use is vaporization. Some places will call it evaporation. Some places will call it boiling. Vaporization is an umbrella term that encompasses all of that. And when a gas turns into a liquid, that's called condensation or condensing. So these are the common ones. But I also, as you saw in the video that was for homework, you saw the carbon dioxide can go from solid to gas through the process of a sublimation. And you also saw in that video when you had the iodine gas turn back into those purple crystals, the bottom of the flask, you saw a deposition. It would be in your best interest to clearly understand these terms and what they mean and how they relate to the phase changes. We will typically just deal with the solid to liquid and liquid to gas phase changes. So we have three scales of temperature. Temperature, as I said, will determine what phase of matter it is. And when I say three scales of temperature, temperature is constant. It's just three different units to measure the same thing. The same way that 12 inches is 1 foot, we have three scales to measure the exact same distance, or in this case, temperature. So Fahrenheit, Celsius, and Kelvin. So Fahrenheit, as you know, is used in the US. Celsius is used in the rest of the world. And Kelvin is what's used in science. Science uses the Kelvin scale because the Kelvin scale can never go negative. Because I said there was a limit as to how cold something could be. If you were able to remove all of the energy from an object, you could never go to negative energy. You would just go to zero. And the cool thing about the Kelvin scale is that the Kelvin scale can never go negative. The coldest possible temperature is 0 Kelvin, and that's called absolute zero. The coldest possible temperature is 0 Kelvin, and it's called absolute zero. There isn't really a limit as to how hot things can get, but there's definitely a limit as to how cold things can get. And don't forget, cold is just the absence of heat. So it's possible to have no heat, but there's no limit to how much heat you could have. So I want to talk about temperature conversions, because there are two equations that I want you to know. If you are converting from Fahrenheit to Celsius, this is the equation, or vice versa, this is the equation that you're going to use. F equals 1.8 C plus 32. So how would it work for if I had 40 degrees Fahrenheit and I wanted to go to Celsius? How would I mathematically do that? Well, I would take the 40 and plug it into the F. Equals 1.8 C plus 32. Now I'm going to treat this as an algebraic equation. I am going to minus 32 from both sides. These are gone. So 40 minus 32 is 8 equals 1.8 C. So to get C by itself, I have to divide both sides by 1.8. That's gone. So I'm just left with 4.44 equals the degrees Celsius. So 40 degrees Celsius is roughly 4.44 degrees Celsius. I'm sorry, 40 degrees Fahrenheit, excuse me, is equal to 4.44 degrees Celsius. Those two temperatures are the same. Well, okay, what if I had 50 degrees Celsius and I want to know how much Fahrenheit that was? I would still use the same equation of Fahrenheit equals 1.8 C plus 32. But this time, instead of plugging into the F, I'm going to take the 50 and plug it into the C. We're solving for the F, so it's going to stay a variable. 1.8 times 50 plus 32. Well, you could just type this in your calculator. 1.8 times 50 is of course 90. Bring it down. F equals 90 plus 32. And when I add 90 and 32, I get so 50 degrees Celsius is exactly the same as 122 degrees Fahrenheit. So 50 degrees Celsius is pretty hot, whereas 40 degrees Fahrenheit is pretty cold. I want you to have a concept as to these temperatures. So that's how you use the Fahrenheit to Celsius equation. But there is another equation that you can use, and that's the Kelvin equation. Kelvin equals Celsius plus 273. Please use the equation that I give you. Please do not use the internet and look up other equations. They are different and they will give you different answers. So if I have 800 degrees Celsius, all I'm going to do is plug the 800 into the C of this equation. So K equals 800 plus 273. Oh, that's not too bad. When I type that in, Oh, Kelvin is 1073. So 1073 Kelvin is equal to 800 Celsius. Oh, that's kind of neat. This equation is a bit easier. But what if I want to go from Kelvin to Celsius? How would that work? Well, let's see. I have K equals C plus 273. It's the same equation. But now what I'm going to do is I am going to plug in the 50K right here. 50 equals C plus 273. I need to get the C by itself, so I'm going to minus 273 from both sides. This cancels. I'm left with C. 50 minus 273 is negative 223. So 50 Kelvin is negative 223 degrees Celsius. That's very, very cold. That's how these equations work. And if I ever wanted to go from Fahrenheit to Kelvin or Kelvin to Fahrenheit, I would just go to Celsius first. I would solve for Celsius, and I would take that answer and plug it into the other equation. But it's only these two equations that get used. Nice. So, I want to be clear about a couple of things, because now I want to talk about the line. Water is a substance, and I said water has a constant melting point and freezing point. And a melting freezing point is when it transitions between a solid and a liquid. So I'm going to quickly label this line. MP, FP, melting point, freezing point. And then between that is going to be the liquid phase. And then here we're going to have boiling point, condensing point. Because that's the point where it transitions between a liquid and a gas. All right, awesome. And again, it makes sense. At higher temperatures, it's going to be more likely a gas. Gas is the highest energy phase of matter, so the higher the temperatures, it's going to be a gas. So I need you just to know all these numbers for water. I'm not going to give them to you. I just need you to know that water freezes at 0, boils at 100, and that's for Celsius. Okay. I also need you to know that it freezes at 32 degrees Fahrenheit and it boils at 212 Fahrenheit. If you don't know that, but you do the Celsius, you could then plug it in the equation. You could solve. And Kelvin is going to be 373 Kelvin. And I'm just out of space, but 273 Kelvin here. I just need you to know these numbers for water, because I need to explain how to interpret the line. So I want to know what phase of matter is at 20 degrees Fahrenheit. So I'm only going to look at the Fahrenheit line. I am going to ignore Kelvin. I'm going to ignore Celsius. So is 20 degrees, this is the question you need to ask yourself, is 20 degrees less than 32? Is 20 degrees between 32 and 212? Or is 20 degrees more than 212? Because if it's less than 32, it would be a solid, because that's this region right here. If it was between 32 and 212, it would be a liquid. And if it was more than 212, it would be a gas. So water at 20 degrees Fahrenheit, 20 is less than 32, that would be a solid. Water at 200 degrees Fahrenheit, okay, 200, okay, 200 is more than 32, but 200 is less than 212. So 200 is going to fall in between these two numbers. And what section is in between these two numbers? It's a liquid. So you just have to assume that it is, you look for the right unit. So we're talking Fahrenheit, so you look at the Fahrenheit numbers, and you look to see where this number falls relative to the numbers that you already put on the line. So at 250 degrees Fahrenheit, 250, well, that's more than 212. That puts it in the gas region. And again, bigger temperatures are more likely to be gases. Smaller temperatures are more likely to be solids. But it's all relative. But I could do the exact same thing with Celsius. Let's just pretend, I don't know, we had something at 40 degrees Celsius, we had something at 0 degrees Celsius, and then we had something at 101 degrees Celsius. Okay, well at 40 degrees Celsius, 40 is between 32 and 212, but that doesn't matter because we're not looking at Fahrenheit anymore. So let's get a new color. Now we're looking here at the Celsius. That's the only thing we're looking at now. So at 40 degrees, is 40 between 0 and 100? Is 40 less than 0? Or is 40 more than 100? Those are the questions you have to ask yourself. Well, since 40 is in between 0 and 100, it's a liquid. Awesome. Okay, 0 degrees Celsius. Oh, that's right on the point. If you were ever at a melting point and freezing point, you have both phases of matter present. What do you mean both phases of matter? You have both the solid and the liquid present. You have because it's transitioning at that temperature. So you have both phases that are next to it present. If you're ever at a melting point or boiling point, you have both phases of matter present. 101 degrees Celsius. Okay, well, if water boils at 100, even if it's just 101, even if it's 101, if it's any degree higher than 100, it's going to be a gas. That's how this works. You just find the line, and we can do the same for Kelvin too. You just figure out where it falls on the line. So what I'm going to ask you is, let's just say an unknown substance boils at 80 degrees Fahrenheit. So I'm going to just solid, melting point, freezing point, liquid. Again, as you add more temperature, it turns from solids to liquids. First it melts, turns to liquids. You continue to add more temperature, then it starts boiling, and then it becomes a gas. So the line will always look like this. So if I say an unknown substance boils at 80 degrees Fahrenheit, 80 degrees Fahrenheit, and melts at 240 Kelvin, well, what I can do is I can use my temperature equations to get C and F here, and I can use my temperature equations to calculate all of those. Wait, Pizzuto, what are you talking about? Well, 240 K, and I know that K equals C plus 273. Oh, so if I'm at 240 K, I know that the melting point is going to be just 240 minus 273. It's going to be negative 33. And I can keep going like this. And now that I know the Celsius, I can go ahead and say Fahrenheit equals 1.8 C plus 32. But the C is actually going to be negative 33. So F equals 1.8 times negative 33 plus 32. Yes. Yes. So I'm typing that in, 1.8 times negative 33 plus 32, and then the Fahrenheit is negative 27.4. Okay, cool. And I can do the same thing over here. I'm going to do that real quick. I'm not just going to do that super quick. 80 equals 1.8 C plus 32. When I minus 32 from both sides, and then divide by 1.8, I hope that you could trust me that the degrees Celsius is 26.67. And then when I go ahead and plug that into the equation for K equals 26.67 plus 273. And then I get essentially 299.67. Okay. So we have our lines. We have our temperatures. So let's just ask a question. Here's a question. At 212 Kelvin, is this a solid, liquid, or gas? Because it says Kelvin, I'm going to look at the kelvins. Is 212 between those numbers, to the left of them, or to the right of them? It's to the left, so it's a solid. Awesome. But here's where it gets a little tricky. When you have negatives. If I had negative 21 degrees Celsius, please pay attention to this. This works exactly like a number line. So if I have negative 21 degrees Celsius, is that going to be to the right or to the left of negative 33? Well, remember, if you're negatives, 0 is to the right. So the smaller the negative, the bigger the number. Negative 21 falls in between these two numbers. That makes it a liquid. Pay attention to the negatives. Pay attention to the negatives. So this Fahrenheit was negative 27.4. So what if I had negative 29 degrees Fahrenheit? Is negative 29 to the left of negative 27 or to the right of negative 27 on the number line? That's the question you need to ask yourself. And I hope you all know that negative 29 is to the left of negative 27.4 of the number line, which makes it a solid. Go over your negatives if you need to, but this is how the line works. So a heating and cooling curve. It works along the same ways. Okay? This is a heating curve. And the heating curves and the cooling curves have 5 parts. Again, as the temperature goes up, the bigger the temperature, the more likely this is going to be a gas, then this is going to be a liquid, and this is going to be a solid. And what's happening is you're warming the solid and then you're melting it. You're warming the liquid and then you're boiling it. And then you're warming the gas. That is fundamentally what is happening here. And the reason why the line goes flat is because that is the point where it's undergoing a phase change, and it remains at a constant temperature at a phase change. So there will always be 5 sections to a heating curve and a cooling curve. You have warming the solid, you have melting, you have warming the liquid, you have boiling, and then you have warming the gas. So what can we do with this? Well, we can get some information. What temperature is the melting line at? Well, let's look. Oh, it's at negative 60. So I could say that the melting point for this is at negative 60. And oh, it's Celsius. Thank you. Look at the units. Okay, the boiling line is right here. So if I go over, oh, it boils at positive 60. So I have the melting point and the boiling point. And if I have the melting point and the boiling point, I can now tell you exactly what phase of matter it would be at any temperature. Okay, well, what if I want to know at 20 degrees? At 20 degrees Celsius. This is what you do. Find 20 degrees. Go over. What part of the graph does it intersect with? It intersects with the liquid. Okay. What about negative 100? Negative 100, well, that intersects with the solid. What about 70? Okay, well, 70 is not here, but 70 is more than 60. So if I go more than 60 and go over, I definitely hit the gas region. That's it. That's all there is to it. So how is it that I could then draw one myself? Well, this is saying it's a cooling curve. And let's just say that the boiling point is 70 degrees Celsius and the melting point is 30 degrees Celsius. A cooling curve is the exact opposite. It starts with cooling a gas. So if you start with a gas, you've got to transition to a liquid first. So this is how it's going to go. It's going to go backwards. So you always start kind of at a high temperature and you come down. And we hit the boiling point first. So we're going to go down from 100 to 70. Flat line at 70. Then, for a little bit, then we're going to go down until we hit 30. Flat line at 30, because down that's the melting point. Down. So what's happening here? We're cooling a gas. We're condensing. Then we're cooling a liquid. And then we're freezing. And then we're cooling a solid. So there are, whether it's a heating curve or a freezing or a cooling curve, you always have 5 sections. And this is always going to be the order of the sections. And the exact same things apply. So from a boiling point, melting point, I could draw a curve. It's going to look exactly like this. The curve always has 2 flat stops because there's only 2 phase transitions. This case from gas to a liquid and from a liquid to a solid. And one more question. What temperature is this at 60 degrees Celsius? At 60 degrees Celsius, it's a liquid. Because it intersects the liquid part of the line. That is all you need to know for the quiz. If you have any questions, please don't hesitate to reach out. Look through the old work, get as much of it done as you can, and good luck. Don't forget to like and subscribe.